Hello, everyone. You know some of the most important equations that describe our universe? Think about the orbit of a planet or the decay of an atom. All right, let's dive in. Today, we're going to tackle one of the biggest challenges in all of science and engineering: how to predict the future. The main tool for this, something called a differential equation. Now, these are basically the mathematical keys that unlock models for, well, just about everything, from planetary orbits to how a guitar string vibrates. The question is, how do we take a simple rule about change and use it to see what happens next? Let's find out. And really, this is the heart of the problem, isn't it? Very often, we know the rule that governs how something changes from one moment to the next, but we have no idea what its actual state is over time. So how do you get from that rule of change to a full-blown prediction of the future? That's the puzzle we're going to solve today. So how do we tackle these big problems? Whether it's the path of a planet, the way your coffee cools down, or how a radioactive particle decays, they're all described by something called a differential equation. Now, these equations don't just hand you the answer. Nope. Instead, they tell you the rate of change at any given moment. To see the whole picture, we need a way to step forward in time, bit by bit, and trace out the entire journey. That's our mission today. Okay, so an ODE is exactly what it sounds like. It's an equation that's all about derivatives. And as you know, derivatives are just rates of change. The tricky part is, it doesn't just hand you the answer. Nope. Instead, it gives you a rule for how a system evolves. Think of it like this. An ODE tells you your speed at every single moment, but it never tells you your actual location. So this is what the problem looks like mathematically. On the left side, that dx over dt term, that's just the rate of change of some quantity we're calling x over some time t. Now on the right, that function f of t comma x, that's our rule. It's telling us that the rate of change depends on both the current time and the current value of x. Our job is to work backwards and figure out the original function, x of t. A rule by itself isn't nearly enough. If I just tell you the rule is go east at 5 miles an hour, where do you actually end up? Well, that completely depends on where you start, right? And that brings us to the second absolutely crucial piece of the puzzle, the initial condition. Look, if we want to find one single unique solution, not a million different possibilities, we have to anchor it somewhere. We have to plant a flag in the ground. And we do that by declaring that at some starting time, let's call it t0, our system has a specific known value, x0. We're going to start with the first and, honestly, the most intuitive approach, which came from the brilliant mind of Leonhard Euler. And his idea was just beautifully simple. He said, to find your next position, you just start where you are, and you add a small step. The direction you go is just the current slope, that's the f part, and you multiply it by how big of a step you want to take, that's h. It's literally like taking one small straight step in the exact direction you're facing at that moment. Okay, so we've got our rule of change, and we've got our starting point. Now what? How do we actually build the solution? Well, trying to solve these things with just a pen and paper can be ridiculously hard, sometimes literally impossible. So instead, we're going to turn to our trusty computers and use a really powerful core strategy to find a numerical answer. The idea behind this strategy is actually beautifully simple. First, instead of thinking about time as this continuous flowing thing, we chop it up into tiny little finite steps. We'll call the size of these steps h. Then, starting from our known point, x0, we use our rule to figure out the next point, x1. Then we use that point to find x2, and so on and so on. We're literally building the solution piece by piece. But here's a word of warning: since we're approximating at each step, tiny errors can creep in and they can add up over time. This image shows it all perfectly. You see that gray curve? That's the true path, the real answer we're trying to find. And the black line? Well, that's Euler's method, trying its best. It's just a bunch of short, straight lines. At each point, it finds the tangent, the direction it's facing, and just follows that for a little while. You can already see the problem, can't you? That black line, it's starting to drift away from reality. And here is the big flaw with Euler's method. Its error is what we call order h, written as O of h. So what does that mean? It means the total error you accumulate is directly proportional to your step size. If you want to put your error in half, you have to take twice as many steps. For any serious scientific work, that's just not going to cut it. It's not efficient enough. Now, what's really cool is that this mathematical idea turns into incredibly simple code. This little Python snippet here is the whole engine. Just look at that second line. It's a direct one-to-one translation of the Euler formula we just saw. We're just calculating the new value of x and adding it to our list. It's super elegant, but as we now know, it's also pretty flawed. Okay, let's get a little more formal for a second. Mathematically, what we're doing in each step is described by an integral. As you can see here, the value at our next step, xn plus 1, is just our current value, xn, plus all the change that's accumulated over that little time step. And that accumulated change, well, that's the integral of our rate function, f of t x. Here's the secret. Every single method we're about to talk about is just a different trick for approximating this one integral. And that right there brings us to the single most important idea in this entire explainer. Seriously, if you remember one thing, make it this. Every numerical method for solving ODEs, from the absolute simplest to the mind-bogglingly complex, is just a different and hopefully better way of estimating the value of that integral. The better our approximation of the integral, the more accurate our final solution is going to be. Simple as that. But what if we could be a little smarter? What if we could find a more representative, sort of average slope for the whole step? And this slide shows two really clever ways to do just that. On the left, we have the modified Euler method, which cleverly uses the slope at the midpoint of the step. And on the right, the improved Euler method averages the slopes from the beginning and the end of the step. Both of these are a huge leap forward in accuracy. Now, these improvements all lead us to the true workhorse of this entire field. This is the method that physicists and engineers really rely on. It's the fourth-order Runge-Kutta method, or, as we all call it, RK4. It is powerful, it's elegant, and it is incredibly accurate. Okay, now I know this formula might look a little intimidating, but don't let it fool you. It's not as scary as it looks. All it's really doing is taking a very, very smart weighted average. It actually calculates 4 different slopes, one at the beginning, 2 cleverly chosen ones in the middle, and one at the end of the step. And then it combines them all using a very specific weighted average. Here's the payoff. The global error for RK4 is order h to the fourth, O of h to the fourth. This is a monumental leap in accuracy. What this means is, if you cut your step size in half, you don't just cut the error in half. You reduce the error by a factor of 2 to the power of 4. That's a factor of 16. That is some serious power. And for any of you who code, this is how it's implemented so elegantly. What you're looking at here is the classic recipe for RK4. You can think of the Euler method as being blindfolded. It feels for the slope once, right at the start, and then walks in that direction for the entire step. The Runge-Kutta methods, on the other hand, are much smarter. They kind of peek ahead. They sample the slope at multiple points inside the step, which gives them a much, much better feel for the true shape of the curve. And this table right here, this shows you exactly why we go through all that extra trouble. That accuracy order tells us how fast the error shrinks as our step size, h, gets smaller. For Euler, the error is proportional to h. So if you put the step size in half, you cut the error in half. Okay, for RK2, the error is proportional to h squared. Have the step size and you quarter the error. Better. But now look at RK4. The error is proportional to h to the fourth power. That means if you have the step size, you reduce the error by a factor of 16. That is a massive, massive improvement. So we've gone on quite a journey, right? From a simple rule of change all the way to incredibly powerful, accurate methods for predicting a system's future. We've basically unlocked the ability to solve a huge class of problems that are just impossible to do by hand. So I'll leave you with this thought. Now that you have these tools in your toolkit, what complex dynamic systems in your own world could you start to model next?